You recall last time we had done the following. We had defined what are randomized algorithms, that is algorithms that can toss random coins and execute according to the outcome of these random coin tosses. Now, using tools such as linearity of expectation, Markov's inequality, and union bound, we were able to, for problems such as max cut and set cover, show that the probability of the algorithms giving unsuitable or not good answer is going to actually be bounded. So this we call the error probability of the algorithm. Okay, and we're going to continue in this vein. We are going to more concentrate on rounding linear programs. Now, regarding last time's lecture, there were a couple of typos in the notes that were posted as I worked them out on the whiteboard. So the Piazza page has got the corrected notes. Okay, so I mentioned where the typos are so that you can see them. Okay, so do look at the notes posted on Piazza. Okay, so this is the plan for today. We are going to look at 3 problems: the maximum independent set problem, the max sat problem, and minimum congestion routing. Okay, so let's start with the problem of maximum independent set. Okay, so in the maximum independent set problem, the input is a graph V comma E. It has weights on the vertices which are non-negative. Okay. As output, you want to output a subset of the vertices, okay, that actually forms an independent set. That is, no edges are contained between the vertices just within S. And of course, the objective that we want to optimize is maximize the weight of the independent set that the problem outputs. Okay. Now this problem is notoriously hard. Getting even n raised to 1 minus epsilon approximation is NP hard. That is, notice that you can trivially output a 1 over n approximation. In the unweighted case. Okay. And getting anything better than 1 over n approximation, this should rather be n raised to minus 1 minus epsilon approximation. Getting anything even slightly better than 1 over n is NP hard. Okay. So by the way, getting a 1 over n approximation is trivial because you can just output a single vertex. And that itself will always be a 1 over n approximation because the maximum size of an independent set in the graph is at most n, which is the number of vertices in the graph. Now here what we'll do is use randomized rounding. To get a 1 over 2 square root m approximation, where m is equal to the number of edges in the graph. So notice that for m is equal to, say, omega n squared, this is close to trivial. Okay, because you get 1 over n approximation asymptotically. But if the graph is sparse, then this is a better approximation. Okay, so as I indicated before, we are going to write a LP for the maximum independent set problem and round it randomly. Okay, round the solution. So what would be an LP for maximum independent set? This is quite easy. The objective is nothing but you have variables xv for each v being a vertex, right? And the objective is maximum summation v in v wv xv subject to the constraints that for all uv in E in the edge set you have that xu plus xv should be at most once. That is, you cannot choose both endpoints of an edge into your independent set. Okay. Of course, this is accompanied by xu is greater than or equal to 0. Okay, so this is the LP relaxation. And we are going to go ahead and round this quantity. So like before, and the algorithm is going to be somewhat similar, but with a slight bit of a clever idea that comes in. So let us start as usual by solving the LP. And you get the optimal solution x star, right? Now x star will have value ZLP. Okay, that is the objective value is ZLP. Now, as I said before, or like it's seen in the set cover problem, a natural way to interpret the values that is given by the optimal LP solution is to look at them as probabilities, right? And we are going to toss random coins based on these probabilities. Now, the small difference is here is, well, you could say that you still go ahead and look at x star v as the probability that v is in the vertex set, but this doesn't really work here immediately. So what we'll do instead, and you will see why this is done, is we are going to define the probabilities as a scaled version of the xv's. Okay. So the probability that a vertex is in the set is what we're going to denote by PV, and that is going to be approximately, or rather exactly, xv by square root n. Okay, so what we're going to do next is to define random variables xv, which is 1 with probability PV and 0 with probability 1 minus PV. Okay, and this is again for all vertices in the graph. Okay, now we go ahead and do the following, define the algorithm based on these random variables. Okay. So the first step in fact is to check whether the weight of any single vertex itself is large enough. And now you do know what the value ZLP is, and you say that if W max is greater than or equal to 1 over 2 square root m times ZLP, again m is the number of edges in the graph. So W max is greater than 1 over 2 square root m times ZLP. Then, because we are just targeting a 1 over 2 square root m approximation, okay, so you just output this single vertex. So this is, we are not even using the random variables defined if one single vertex has got large weight in itself. Okay, and clearly a single vertex is an independent set. Now what if this is not the case? Well, then we go ahead and do what we always do, that is toss the coins xv for each v in the vertex set. If xv equal to 1, I'm going to call this set I. Okay, and if xv turns out to be 0, you just don't include the vertex v into your target independent set. So of course this starts off with I being the empty set. Okay. So now what? Well, we cannot just output I as it is, simply because there is a chance that all the coins turn up 1, so I is not really an independent set at all. So we need to do a pruning process that for each edge E which is in your set, each edge E in the edge set, such that U and V, let us say the edge has got endpoints U and V, okay, and U is the independent set candidate and V is also part of I. Well, of course, we need to do something. We need to remove one after two. What we're going to do is remove both of them. Okay. And finally, after this pruning step, by definition, we have an independent set, and so you output I. Okay. So I hope the algorithm is clear. Again, if no single vertex has got large weight, then you go ahead, toss these coins, include some candidate vertices in your set, and then you do a pruning procedure to ensure that the set that you will finally output is indeed an independent set. Okay, so let's go ahead and analyze this algorithm and see what is the expected value of the weight of I. So we are going to introduce some notation here just to make things clear. We are going to call I1 as the state of I, or rather, let me just call it I before the pruning step. Okay. And I2 is I after the pruning step. And clearly, this may not be an independent set. And this is an independent set. Okay. And so correspondingly, we had these random variables xv's that we had introduced. Okay. So similarly, we are going to introduce pairwise random variables, which we'll call ZUV. So this is again defined ZUV is 1 if UV is in E, that is UV is an edge, and okay, so basically ZUV denotes those edges that were present in my set before the pruning occurred. Okay. And notice that again ZUV is a random variable because what edges are present in the set I is a random variable depending on the outcomes of the XUs that are there. Okay. So clearly if ZUV is equal to 1, it means that U and V were pruned out from the set. So using the variables XU and XV, we can now express what is the algorithmic value. So initially we had the vertices are included, so this counts the weight of I1, okay, minus, well, there were vertices removed and these correspond to edges, and the edges were indicated by ZU, right? So this is the removed vertices. Notice that there's no double counting over here in this of the vertices that were removed because we are removing both endpoints, okay, of an edge that is present in my non-pruned independent set. Okay, cool. So right now what we want to do here is figure out what the expected value of the algorithm's output is. Is by linearity of expectation, this is just summation U element of V, WU, SU, right? So this is simple enough by linearity of expectation. Now, all of these, both XU and ZUVs, are indicator random variables, right? So their expectation is equal to the probability that they take the value 1. So here, we know that XU is 1 with probability just PU by, rather, with PU, which we have defined as XU by square root M, right? And for ZUV, well, these coins for every vertex were tossed independently, and therefore this thing, the probability that ZUV is 1, that is both U and V are included in my initial I, is PU times PV, which becomes XU times XV by M. Okay. So substituting back these values, we get rather I say that because you have solved the LPs and we are using it to round, this is all XU stars and XV stars. Okay. Now, in order to simplify this expression and make it look something like the LP objective value, what we're going to do is simplify this expression over here. And how do we simplify this expression? We use the fact that AB is less than equal to a square plus b square by 2, which is your favorite Cauchy-Schwarz inequality, or AMGM, or whatever you would like to call it. So what we'll get is that this is equal to summation, first part remains as it is, this becomes a greater than equal to because it appears with a negative sign over here. Right? And now, as we have done before, we are going to cleverly utilize the fact that the x stars are actually feasible. So this we're going to say is greater than or equal to u and v. The first term remains exactly the same till we get round to it. Meanwhile, we just replace the squares by the original quantities, and this works because the xu stars are all bounded between 0 and 1. Okay, therefore xu star squares is less than or equal to xu star. Therefore this inequality holds. And now what we know about this linear form is that because uv is an edge, xu star plus xv star is less than or equal to 1. Okay. So substituting this back, what we get is this quantity is greater than or equal to square root n minus, now all you have is uv in e wu plus wv by 2n, right? Okay, so now suppose we introduce the notation dv to be the degree of vertex v in G. Okay. Then we have that summation uv in E w plus wv by 2m, nothing but, well, how much time is every single vertex counted? Well, we are counting it for every edge that is incident upon it. So this is 1 over 2m summation w du for just u and v. So we are just working with the second term over here. And now this thing here is, of course, this is nothing but a weighted average of WUs. Okay, and why do I call this a weighted average? Since summation u du is exactly equal to 2n. Okay, the sum of all the degrees in the graph is exactly equal to twice times the number of edges. Okay. So this term is for sure an average which is less than equal to W max, which is less than equal to as we know, ZLP by 2 square root m, because we only did all this random coin tossing in case B, which was when no single vertex had got weight larger than ZLP by 2 square. So this gives us that the expected value of the algorithm is summation over u wu x u star by square root m, where this is greater than equal to minus ZLP by 2 square root m. And this greater than equal to because notice that at every point the inequalities with respect to the second term we upper bounded, right? So this, if you notice, the first term is just ZLP divided by square root m minus ZLP divided by 2 square root m, and this whole thing greater than equal to, in fact this is exactly equal to ZLP by 2 square root m, which we know opt. So in the first case, if there existed V such that WV is greater than 2 square root m opt, implies we surely have, without any randomness, the algorithm was greater than 1 over 2 square root m times opt. If not, then using this random coin process, what you have found is that the expected value or the expected weight of the independent set output by the algorithm is at least 1 over 2 square root m times opt. So in both cases, this is a randomized 1 over 2 square root m approximation. Okay. So we see that the rounding scheme here was slightly cleverer than what we had seen in the set cover example. Over there, we just needed to look at the XU stars or XS stars in that case as probabilities and toss random coins and do the obvious thing. Here, we need to look at two cases and be a bit clever between in the analysis also. Okay, so I hope this procedure is clear. With that, let's move on to the next problem that I want to talk about, which is the max-sat problem. Okay, so this is quite a well-known famous problem. In fact, you might all have heard of the max 3-sat problem, and this is a straightforward generalization of that. Okay. So as input, what you're given is n variables. There are all Boolean variables, that is, they take values in 0 or 1, and you're given a set of clauses. Say there are m clauses, Cm. Every clause, let us take a Cj, which is a clause, looks like an OR of certain xi's. So as a simple example, let us say that Cj might look like x1 or x5 or x7 or x10 bar. We're saying that Cj has length Lj. Okay, what that means is there are Lj literals occurring in clause Cj. Okay, so for instance, the Cj presented over here has got length 4. What do I mean by a literal? I mean a variable or its negation. Okay, so both x1, x5, x7 and x10 bar are literals. So there are a total of 2n possible literals, every variable or its complement, and they occur in disjunction form in clauses. Okay, the clauses are not of fixed length. Okay, so every Cj can have a different Lj length over here. That's why it's called the max sat problem. If the clause length was restricted to some k for every clause, then it would be called the max k-sat problem. So what is the output over here? We want, of course, to output an assignment to the variables. And what is the goal? That is, what is the objective? The assignment must satisfy as many clauses as possible. Okay, that is, it could be that a certain assignment does satisfy clause C1 and C2 but does not satisfy C3 and C4. You want to find an assignment that satisfies as many clauses as possible. Of course, the decision version of the problem in the original setting would have been, is there an assignment that satisfies all the clauses? Okay, and that is the SAT problem. So just to make this clear, notice that Cj is 1 if